We're going to take an example, a look at an example on contingency tables with small expected values. What we mean by small expected values is less than 5. Okay. The question, we're looking at gender, male or female, and choice of sport. It says year 12 students at Carlton College participate in one of 4 sports: squash, badminton, archery or hockey. And we're asked to test at the 5% significance level to determine if a subject choice is independent of gender. We've also got to interpret our results as it relates to the students studying hockey. Okay. First, we'll just maybe have a little look and get a feel for like what's going on. Like, is there going to be an association between these two things, or are they completely independent? Is there no association? Looks to me like there's an awful lot of female students who've chosen hockey, but it's not just about comparing the raw values, it's the proportional values that we've got to compare. And that's where this chi-squared calculation comes in. It calculates the expected values, which are proportional representations. And then the test statistic tells us a measure of how far away what actually happened and what we'd expect to happen. Okay, so start with the hypothesis. No association between gender and sport choice. H1, there is an association. I'm going to say ... Please don't do that in the exam, but I'm going to do it for this one. Okay. So let's calculate our expected values. I've not put the totals on, but they are on the question in the sheet. The expected, let's do it for the 5. So it would be 70 times by 9 divided by 180. And that gives us 3.5. I probably should have mentioned this at the start, by the way. I knew this was going to happen. Like, it's not always immediately obvious, but like, see, if you look at squash, there's like a very small amount of students who've chosen squash. So because the observed values are small, the expected values are also going to be small, aren't they? And clearly the total doesn't even add up to 10. So proportionally, there's no way that that could ever give us expected values which are more than 5. So when we say small, by the way, we're looking for an expected value which is less than 5. So if this happens, you don't need to carry on with the question and calculate all the expected values. You could say, as one of the expected values is less than 5, combine the data. Be careful, alright? It might be probably obvious for this one, but just use a bit of common sense. We've got to combine squash with something. Now, the choice is badminton, archery or hockey. What is squash most similar to? Like, could you play a bit of squash and shoot some arrows inside? Or, you know, hockey involves a stick and a ball. Clearly, we're going to combine squash and badminton together and just call it racket sports. Okay, squash and badminton. Okay. Now all that we do here is we just add them together, write out a new table. So 5 plus 16, we've got 21, then we've got 30, and we've got 19. 4 female squash, 20 badminton female, so that'd be 24. And 53. So this is going to be the table that forms our calculation. Okay, so now let's go on to statistics, test, chi, two-way. The dimensions of my matrix now are 3 by 2, because it's, wait there, no it's not, is it? It's 2 rows, 3 columns, so I'm going to change my dimension 2 rows, 3 columns, enter my new observed values. So 21, 30, 19, 24, 33, 53. Press exit twice and then press execute. Let's check our matrix of expected values. I should, I suppose, just to make sure I've done that right, calculate manually one of these new expected values. So the new totals, say if we were calculating the expected value for this one, let me just do that. Okay, so we get 17.5. One other thing as well, by the way, that is I've not mentioned, if you would have like actually gone through and written all the expected values down, it's not like a massive waste of time, because when you combine the data together, you add the observed values, and also what happens if I'd have known what those 2 expected values were, I'll just add the 2 expected values, and especially without the graphical calculator, it saves a lot of time. You don't want to do 8 calculations for expected values and then 6 more. Like, the only thing that happens when you combine the data is we add the observed and we add the expected. Anyway, so we've got 17.5. 24.5, 28, 38.5, 44, and 27.5. Okay, so already I'm thinking, like, it seems to me like, you know, you've got more females than what you would have expected. So because there's quite a discrepancy between these 2 things, it's probably going to be leading us to say that there is an association. Okay, but let's see, we'll have to do the calculation. So my chi-squared test is the sum observed minus expected squared divided by expected. You don't need to write that out each time, but you do need to show some method. Okay, so for this first one, observed minus expected divided by expected squared plus dot 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 dot. So my chi-squared test would equal so you want to go back to this screen, it'll tell you the chi-squared test. I could have written that down at the beginning when we got the, once we'd pressed that execute once, but I'm just not having enough space on the board, so you guys can also make a note of that, but just make sure you show the method. So the chi-squared test is 7.8996. Okay, degrees of freedom again is 2 for this question. Rows minus 1, so 2 minus 1. Times by columns minus 1. So the degrees of freedom is equal to 2. I know I didn't mention degrees of freedom in the last video, but basically all the degrees of freedom tells you is, like, because we know all the totals, if I knew like 2 values, or like 2 observed values or 2 expected values, that would be enough information to fill in everything else. If you think about it, if I knew what each of these totals were, which we do, don't we? Degrees of freedom tells you how many pieces of the data that you need to know to be able to like fill in everything else. If I just knew 2 values and I knew the totals as well, everything else would be fixed. Okay, so can you see that if I knew what that total was and I knew there was 21, you could easily figure out that one was 24. So once I knew that one was 24, if I knew that one was 30 and I knew what that total was, I could figure out that was 33. I knew those 2, I knew that total, I could figure out that one. I know them all, I can figure out that one. Or you don't need to understand that for the course, but it just, instead of it just being like a random number, the degrees of freedom gives you like an amount of uncertainty within the calculation. Okay, so we've got this test statistic, we need our critical value, and we're testing at the 5%. So it's a 5% test, degrees of freedom is equal to 2. It's going to be the same critical value from the last video, but let me just show you how to find it. Okay, so we go back and we go on to distribution, chi, inverse chi. Area 0.05 because it's 5%. Degrees of freedom 2, press execute, and we get 5.9915. So now we've just got to compare these two. I would strongly recommend you draw a diagram because it helps the examiner to see that you understand this topic, instead of just like, there's two numbers, write my conclusion. You know, you have to justify what's going on. So the the critical value was 5.9915. That would be H0, that would be H1. What actually happened, our test stat, this is taken, don't forget, this is taken from the data in the question. So our test stat, 7.8996, it's going to lead me to go with H1. In other words, we're going to reject H0, and we're going to say that there is an association. One thing I forgot to do on the last one as well, we should probably write as well, 5.9915. Just like make it crystal clear that you're comparing the two numbers together. Because the test stat's bigger, we would reject H0 at the 5% level. So comments, always refer to H0 first, reject H0, and then comments in context, so the evidence suggests association between gender and sport choice. Specifically, we're asked to interpret that in relation to hockey, aren't we? Okay, so if we look at our observed and expected for hockey, we could say more female than expected. Choose hockey. You could also say fewer male than expected. Okay. Sorry. Okay, I'm going to add an extra little part as well, just because on both of the videos we've done, we've rejected. If we were testing at a 1% significance level, because that might be asked as well, essentially what that means is we need to be 99% sure of our conclusion. At lower significance level means it's basically tougher to say that actually, you know what, there's a link. You need a lot of evidence to say that there's an association between two things. Like, we need to be 99% sure that there's a link. If we're testing at the 5% level, we're 95% sure that there's a link between these two things. If we were doing a 1% significance level test, let's see what our critical value would look like. Okay, so we're testing 1% with degrees of freedom equal to 2. So distribution chi, inverse, 1%, area 0.01, degrees of freedom 2. And that gives me 9.2103. So look at how this would affect. The critical value is 9.2103. The test stat that we got from our data, remember that tells you the difference between your observed and expected. It was 7.8996. So if this was a 1% test at 1% significance level, our conclusion would be different. We'd still be in the H0s. There's not enough evidence. Like, we'd need to be all the way over there if we were going to go with H1. Because we're still in this region here, there's not enough evidence at the 1% level. So I'll show you what that conclusion would look like. So I'd say, first of all, compare the numbers. And we will accept H naught at the 1% level. Don't say that there's no association between the two things. Like, I know H naught, right? H naught says there's no association, but like the test that's all the way over there, it looks to me like there is an association. There's just not enough evidence for us to say that at the 1% level. Like, I can't be 99% sure of my conclusion. So I would say insufficient evidence to suggest association between gender and sport choice. And that is, like, I think this is the best way to answer this scenario if this happens. Accept H naught, but don't just write no evidence, no association. Like, show a little bit more, sort of a little bit more maturity in the way that you're interpreting what's going on. Then it looks to me like there is evidence, there's an association, but there's not enough evidence insufficient evidence to suggest. That'd be a good way to answer that question. Thanks, guys.